So thanks a lot for inviting me. Today I'm going to talk about the complexity of a problem related to the gradient descent algorithm and the consequences on some complexity classes. This is joint work with John Fernley and Rahul Savani from the University of Liverpool and Paul Goldberg from the University of Oxford. So I will try to make breaks throughout the talk to allow for questions, but you should also feel free to just interrupt me at any moment if you have a question. So let's start by just considering the following classical optimization problem. We have a function f that we want to minimize over some compact domain, like for example, the unit hypercube. And we're interested in this problem for nice functions f, where by nice, I mean essentially smooth, continuous differentiable. So this problem is ubiquitous in practice, and has also been studied a lot in the optimization literature. And of course, it is known that this problem is, from a theoretical standpoint, hard, namely, it is NP hard. And in fact, this NP hardness holds even for very, very simple functions f, namely even when f is just a quadratic polynomial, this problem is already NP hard. In practice, though, what people do is that they still have to solve this problem somehow, or at least attempt to do so. And one very popular technique is the gradient descent algorithm. So the gradient descent algorithm is very simple. The idea is just you have this iterative process where the next iterate is obtained from the previous one by going in the opposite direction of the gradient in some step size, which is denoted by eta here. So let's take a look at the picture. So imagine that I start off at this point over here. What do? I just use the local information I have, which is the gradient, and I go in the opposite direction of the gradient, which locally, given the local information I have, is the optimal thing to do, given that information. So for example, one gradient descent step could look like this, then it could look like this, and like this, and one would hope that ultimately you end up in a minimum. Now this is, really used in practice, various versions of this gradient descent algorithm. But from a theoretical perspective, the gradient descent algorithm is not guaranteed to solve this minimization problem. And the reason for this is that it essentially can get stuck at stationary points. It's only guaranteed to output a stationary point. If you look at the update rule over here, if the gradient happens to be 0, then you don't move, you stay at the point where you were. And now stationary points are not necessarily global minima of the optimization problem. It could be local minima, but in fact, even local maxima are stationary points. So here, because we're looking at a constrained domain, to be a bit more specific, whenever I say stationary point, I actually mean a so-called Karush-Kuhn-Tucker KKT point, but you can just think of it as a stationary point. It's just the definition is adapted so that it also works on the boundary of the domain. So as I said, even a local maximum, like the top of the mountain over here, the gradient there is 0. So if gradient descent starts there, it will just stay there and output that point. So what that means is that gradient descent is not guaranteed to output a minimum of this optimization problem. It outputs some weaker solution concept. And the solution concept is essentially this, a stationary point. And so the question we ask in this project, is there a question?
Yeah, because of the discreteness of the size of the step, it also may alternate around the stationary point or something like that, right? It doesn't even have to reach a stationary point.
Yes, so depending on the parameters of the function, like if you have a bound on the Lipschitzness of the gradient, by picking the step size appropriately, you can ensure that you will converge towards a stationary point.
Okay, so if you have a smoothness bound.
Yes, exactly. So yes, exactly. We study this problem for nice functions f, where we have bounds on the Lipschitz constants of gradients and stuff like this. And so the question we ask in this project is, okay, this optimization problem is NP hard, but what about the problem that is actually solved by gradient descent? namely the problem of finding a stationary point. What is the complexity of that problem? Another way to, to formulate it is to say, okay, what is the complexity of finding a gradient descent solution? Or again, in other words, what is the complexity of finding a point where gradient descent terminates? And so if you want to study this question, you obviously have to formalize this somehow. So how do we formalize this computational problem? The input to the problem is going to be a continuously differentiable function on the unit hypercube. We'll also be given a step size eta and a precision epsilon. And the goal is to find a point where gradient descent terminates. So before I talk about how the input is represented, let me first try to explain how we interpret that goal. What does it mean, a point where gradient descent terminates? Because it turns out that there are various ways to say, to define where gradient descent terminates. In other words, like stopping criteria for gradient descent. So the first one we're going to look at is the problem we call GD local search. And here the idea is, we think of it as, okay, we stop gradient descent as soon as the next iterate does not decrease f by enough. So it decreases f by most epsilon. In other words, we think of it as we're just running gradient descent. And if we end up at a point where the next iterate only improves the value of f by epsilon, then we just stop at that point. And so the computational problem is find any point where this holds, where the next iterate would not improve us by enough. So this is viewing gradient descent as a local search kind of algorithm, but you can also view the gradient descent update rule as a function of which you might be interested in finding a fixed point. So in that case, you might use the stopping criterion. I will stop when the next iterate is very, very close to the current iterate. In other words, performing an update according to the gradient descent rule just moves my current point by very little. So that's a second way to define where gradient descent would terminate. Fortunately, it doesn't matter which one you prefer, because you can show that the computational problems are polynomial time equivalent. So it doesn't matter which one we pick, the definition of the problem is robust. And ultimately, the reason for this is that we're looking for a stationary point. And this is what binds these two things together. Is there a question?
Yeah. How does this polynomial time depends on the smoothness parameter of the smoothness affects it just by constant or well?
Yeah, so I don't remember exactly how the parameters work in, but here I'm just looking at the setting where everything is given in the input. The step size is given in the input. The Lipschitz constant is given in the input. And so in that sense, as long as these things are just polynomial and computable from the old parameters, the problems are going to be polynomial time equivalent.
Another question, sorry if I may.
Yes.
So you also have a choice of the starting point. So you're here really just looking for any possible termination point. Or...
Worst case.
Okay.
It's for worst case, right? You're studying worst case.
Yes, exactly. You can think of it like this. Or I'm just using, gradient descent as a motivation for studying the complexity of finding a stationary point. Ultimately, you can just interpret both these problems as just, I give you a function, find a stationary point of the function. This is the same problem, essentially. So I've defined what the solution is here, but I haven't told you what exactly the model in which we study this is. So usually in optimization, people like to study these kinds of problems, the so-called black box model, where you can query the function value and the gradient value. But here we study this problem in the so-called white box model, where the function is given explicitly to you. In other words, you can think of it as having the code for the function given to you. Here to be concrete, we're going to assume that f and the gradient of f are given as arithmetic or algebraic circuits. So I explicitly give to you in the input the description of a circuit that computes the function f and its gradient. And what that means is that now all of the input is just white box, and you can study this problem in the standard Turing machine model. It's no longer a query model where you count the number of queries. It's the standard Turing machine model with complexity classes, etc. Now, if you look at this problem, there is one obvious algorithm that solves it, which is just running gradient descent. Pick some point and just start running gradient descent there. So how fast is gradient descent on this problem? And it is known that the running time is essentially, if we ignore the other parameters, it's polynomial in 1 over epsilon. And perhaps in practice, this is pretty good, depending on how small the precision is that you want. But in the way in which I define the problem here, with those things in the input, the step size and the precision, these things are given, in the standard binary encoding. And so something that's efficient in 1 over epsilon is not actually polynomial time. We would need something that's polynomial in 1 over log of epsilon. So this is doesn't correspond to an algorithm that's polynomial for this problem. And so we can think of this project as asking the question, can we solve this in log 1 over epsilon? Can we solve this problem as I've defined it in the standard Turing machine model in polynomial time? And you might ask, okay, maybe is this too much to ask for to be able to solve such a problem in log 1 over epsilon? But if we're in the special case where f is a convex function, then we know that this is possible using the ellipsoid algorithm. And so the question can also be asked as, what happens if f is not convex? What is the complexity of this problem then? Is there any hope of solving it as fast as in the convex setting? Or is it computationally hard in the standard Turing machine model? So I think this is a good point for me to take a break if there are questions about the definition of the problem. We already had a few.
So what about the black box model of this question? Is this hard or?
Yes, so there are some lower bounds, but the complexity is not yet fully understood, not tight, the upper with the lower bounds. But yes, there are essentially lower bounds that tell you that in terms of the queries, you cannot go down to log 1 over epsilon dependency. It's going to be 1 over epsilon dependency.
Can you maybe repeat the distinction between this formulation and the formulation that's NP complete?
Mm-hmm. So the NP complete formulation just asks you to find a minimum of the function f, a global minimum of the function f. Whereas here, I'm just looking for equivalently a stationary point, namely a point where the gradient is 0, or equivalently a point where gradients and terminates as defined on the previous slide.
So global versus local is the real distinction?
This is there's a global minimum, then there's local minimum, and then there is even more special stationary point. So every global minimum is also local minimum, and every local minimum is also stationary point, but not the other way. So every stationary point is not necessarily a local minimum. And so
will this distinction be essential for the result?
Sorry?
Will this distinction between local minimum and stationary point would be essential for your result?
So because local minimum is a special case of a stationary point, the hardness result still holds. But for the upper bound, looking for a local minimum, it's not even clear what the, it's not going to lie in the class in which we study this class of total search problems, because we don't know how to check if something is a local minimum efficiently, whereas we can check efficiently if something is a stationary point. In fact, it's known as checking if something is a local minimum, even for quadratic functions f, is co-NP hard. So we don't know how to, it's not going to be in the same kind of a universe of classes, the local minimum problem, because you cannot verify solutions efficiently. So that's the advantage of this kind of solution concept, is that you can verify it efficiently. Any more questions about the definitions? Okay, then next I'm going to introduce the classes of interest in order to study this problem. And I'll start by just listing some interesting natural computational problems that have something in common with our gradient descent problem that we want to study. So the first one is the problem Nash. I give you a bimatrix game, and you have to compute a mixed Nash equilibrium of that game. Another problem is also very famous, factoring. I give you a number, compute a prime factor of that number. The problem that I call Brouwer here, given a continuous function, mapping, let's say, the unit cube to itself, compute a fixed point of that function. A special case of that problem, if the function is not only continuous but also contracting, then compute again the fixed point, and it is unique in that case by Banach's fixed point theorem. Then a problem about congestion games. If you don't know what congestion games, you just think of these as games that are used to model incentives in traffic. That's what they're mostly used for. So here the computational problem is compute a pure Nash equilibrium of a congestion game that I've given you in the input. And finally, in this list, there is a gradient descent problem. And so what do all of these problems have in common? And what they have in common is that they are all NP total search problems, abbreviated as TFNP. And that's because they have two crucial properties. The first one is that they are total. For any instance of one of these problems, there always exists a solution. That is mathematically guaranteed that there exists a solution. And the problems are in NP, or rather the search version of NP, in the sense that if I give you a candidate solution, you can verify in polynomial time if it is a solution or not. And this is why we use this stationary point solution concept as opposed to local minimum, because for local minimum, we don't know how to do this. So the problem would not lie in this class. So let me quickly go over the problems to quickly say why they are total, why they have this first property. So for the Nash problem, this is essentially known by so-called Nash's theorem, which says that every game has a mixed Nash equilibrium. For factoring, this is a fact that we all know. Every number that's at least as large as 2 will have some prime factor. The problem called Brouwer, it's called that way because there is a topological theorem, Brouwer's fixed point theorem, that guarantees that such a fixed point will exist. For the problem contraction, follows by Banach's fixed point theorem, which tells you that there exists a fixed point, which is in fact unique. And for the pure congestion problem, this is a well-known result in the theory of congestion games, that these games that have more structure than the general games studied in the Nash problem, that these games even have a pure Nash equilibrium, always. And finally, for a gradient descent problem, why does it always have a solution? Well, since we're working on a compact bounded domain, it means that there exists a minimum of the function, which is in particular local minimum, which is in particular a stationary point. So there definitely will exist at least one solution. And because our solution concept is stationary points, these solutions are also easy to verify in polynomial time. So this holds also for the other problems, and they all lie in this class TFNP. Now, the other thing that these problems have in common is that we don't know how to solve them in polynomial time. And so a natural thing to ask then is, okay, how can we provide evidence that they are inherently hard to solve? And the first thing one might try to attempt is, okay, let's prove that these problems are NP hard. And as it turns out, this is actually probably not an option here, because if any of these problems was NP hard, that would immediately imply that co-NP equals NP. So let me explain this in a bit more detail. So this class TFNP, it was defined by Megiddo and Papadimitriou in 91. And it's the class of total NP search problems. And so 3 things to remember. First of all, these are search problems as opposed to decision problems. So here we're looking for a solution, not just a yes/no answer. They are in NP in the sense that the candidate solution can be checked in polynomial time, and they are total. There's a mathematical guarantee that for any instance, there exists at least one solution. This class is interesting because in a certain sense, it lies between P and NP, or rather the search versions of these classes. And so when you have problems in there that are believed to be hard, they are in a certain sense NP intermediate problems. As I said, a lot of problems in TFNP are seemingly hard. We don't know how to solve them. And so we like to provide evidence that these problems are indeed hard. And so I mentioned that the first thing that one might think of would probably not work. If you prove that some TFNP problem is NP hard, then you have also shown that NP equals co-NP. And actually, this is a pretty simple argument. Let me just do a one-line sketch of that. Assume that you had a polynomial time reduction from 3-sat to Nash. Then you could use that reduction to get small efficient certificates, even for the unsatisfiable instances of 3-sat. Just because Nash always has a solution, and you can use a certificate for the Nash solution as a certificate for the unsatisfiability of 3-sat. So this is not really an option. What's the next best thing we could hope for? Well, let's show that, I don't know, Nash is as hard as any other problem in TFNP. Let's prove that it's TFNP complete.
Alex?
Yes?
Yeah, so the intersection of search versions of NP and co-NP is in TFNP, right?
Yes, there's a way to transform problems like that, yes.
I mean, the problem will be find either a witness of that it's in the language or find a witness that it's not in the language.
Yes.
Will always exist, and okay. So it contains NP intersect co-NP.
Yes, I believe that was already observed in the by Papadimitriou, or even by Megiddo and Papadimitriou. So it is actually believed that no TFNP complete problems exist. And that's essentially because of how general this TFNP class is, right? Because of the way it's defined semantically, by saying it contains all the problems that are total, in a certain sense that contains all the possible mathematical proofs of such theorems of existence. And as a result, people don't believe that there should be one problem that captures all of that. So it seems like we're stuck. So what can we do to provide evidence that some TFNP problems are hard? And so what Papadimitriou proposed around 30 years ago is to study the landscape inside this class TFNP. Since this class is not easy to work with, we cannot prove completeness results for it. Let's try to define subclasses that are nicer, that are syntactic, that have nice complete problems. And let's try to classify the problems that we care about, Nash, gradient descent, whatever, in terms of these subclasses to understand where they lie and to just organize the problems into subclasses so that we can compare their complexities, saying, oh, if this problem is solvable in polynomial time, then this whole other bunch of problems will also be solvable. So various classes have been defined. I'll just mention a few here. So there's a class that's called PPP. And this class essentially contains all the TFNP problems where the totality, so the guarantee for the existence of a solution, can be proved by a pigeonhole argument. There's another class that's called PPA, which contains all the problems where the existence of a solution can be proved by using a parity argument, like, for example, the handshaking lemma. It also has a nice characterization in terms of a topological theorem. So there's this well-known topological theorem, the Borsuk-Ulam theorem. And it turns out that it is this computational problem associated to this theorem is PPA complete. So the class also has a topological characterization. By far, the two more successful and famous classes are the ones I'm going to mention next. The first one is PLS. PLS contains all the problems where totality follows by some kind of a local search argument. And the class has been very successful in capturing the complexity of local optimization problems. So I've put two complete problems here. The pure congestion problem that I had on the previous slide, namely finding a pure Nash equilibrium of a congestion game, that is known to be complete for this class PLS. Another problem is local max cut. I give you a graph and I ask you to graph with weighted edges, and I ask to find a max cut that is local up to optimal up to local changes, like swapping one vertex from one side to the other. This problem is also known to be PLS complete, and there are many other local optimization problems that are known to be PLS complete. That's the first quite successful class, and the second one is PPAD. So PPAD contains problems where the totality follows by some kind of a directed graph argument. I won't explain what it is exactly because we'll see it a bit later in the talk. And it is perhaps most famously known, this class PPAD, because the Nash problem is complete for this class. And just like PPA, the class also has a nice characterization in terms of a topological problem, namely the Brouwer problem, which is based on Brouwer's fixed point theorem, is complete for PPAD. There's one important problem that was on the list of problems that I didn't mention, and that's factoring. What do we know about factoring? Well, the truth is we don't know that much. We know that it lies in PPA and in PPP, but only under randomized reductions. That's why I've put it here, halfway in. But we don't really have any lower bound, any hardness result in terms of any of these classes. And so, factoring could lie in PPAD or not, we don't know. And this is obviously, a big open question. Where does factoring lie in this landscape? So an obvious question to ask is, okay, so Nash is PPAD complete, and that is interpreted as saying that Nash is computationally hard, that we should not expect a polynomial time algorithm. Why is that? Why is a PPAD completeness result or a PLS completeness result interpreted as computational hardness, computational intractability? And so I will list 3 reasons here, more or less convincing. So the first one is simply there are many seemingly hard problems that lie in these classes, PPAD, PLS, etc. And by seemingly hard, I mean problems that occur naturally and that were studied by a lot of people who were unable to come up with a polynomial time algorithm. So that's the first kind of evidence that one might use. Second one is that there are oracle separations between the classes and also between the classes and P. And so in that sense, that also provides some evidence. And the third kind of evidence is that there are various results showing hardness under cryptographic assumptions. I'm not an expert on this, but I believe that the cryptographic assumptions are not completely standard yet, under which we know the hardness, but they are getting better and better. So this seems like a pretty good reason to believe that these classes are hard. Let me maybe take a break here with the classes and ask if there are any questions. Okay. So now the obvious question to ask is, okay, let's get back to our problem of interest, the gradient descent problem. Where does it lie in this picture? And it turns out that it's not too hard to show that it lies in both PPAD and in PLS. In other words, in their intersection. And let me briefly explain why. So here I've zoomed in to the picture. I'm only showing PPAD and PLS. PPAD with its 2 complete problems, Brouwer and Nash, and PLS with 2 other complete problems here. So remember that we had these different formulations of our gradient descent problem. But I told you it doesn't matter which one you pick, they are polynomial time equivalent. So here we're going to use this. If you consider the formulation that we had, which I call the GD fixed point formulation, where essentially you stop gradient descent if the next iterate is epsilon close to the current one. So you view the gradient descent algorithm as a dynamics and you just look at a fixed point, then it's actually easy to see that this is a special case of the Brouwer fixed point problem. And as a result, this GD fixed point problem will reduce to Brouwer. And so this problem lies in PPAD. The other formulation that I gave you was what I call GD local search, where you viewed gradient descent more like a local search algorithm. And you thought of it as stopping if the next iterate does not improve the value by more than epsilon. And if you look at this formulation of the problem, then it's also easy to see this as a special case of local search. And as a result, you can show that the problem lies in the class PLS. But as I told you, these 2 problems are actually polynomial time equivalent. So that means that the gradient descent problem lies in both PPAD and in PLS, so it lies in the intersection.
Alex?
Yes?
Yeah, the algorithm is not, any algorithm for this problem, the gradient descent, is not restricted to use the gradient descent algorithm, right?
Absolutely, yes.
So what is the value of the parameter eta, which is given?
Yes,
That's
so the
accurate you want, but what is the value of the eta, which is given if you are not using it as part of a gradient descent?
yes, so you use it in the definition of the problem. Here, right? When you say, find me a point where the next iterate does not improve the value by more than epsilon, the next iterate is defined by using this formula, which includes eta.
But it's not used in the GD fixed point definition.
There is the same. This x prime is again defined like this.
Sorry, x prime. Yeah, good. Okay, very good.
But again, you can think of this problem. You can also define the problem of just finding a stationary point, and its polynomial time equivalent to that. And there's no eta. Just when you define a problem.
Yeah, so you can think of this question is given without the eta.
Yes, exactly. Exactly. You can think of it as a problem of just finding a stationary point. And then there's no eta in the anywhere.
And now you have the function and its gradient given as arithmetic circuits. Suppose you added also the Hessian. Does it change the complexity results that you have?
That's a good question. I believe it shouldn't change anything, no. You will have to, the functions we construct in our hardness, which I'll talk a bit about later in the talk, they're only continuously differentiable. So you'd have to use some kind of better interpolation to get a function that's twice differentiable, but that won't really change anything.
Okay. So when you said the function is given as an arithmetic circuit, so it doesn't have to be a polynomial, you can have gates that are other functions?
Yes, very good question. Yes. So here I mean arithmetic circuit, no, more general than just the classical ones. So we also allow other gates like a comparison gate, for example, or you can allow max and min. So, more general algebraic circuits. Ultimately, though, it turns out that the complexity of the problem is the same, even if you just say f should be a polynomial of degree 5 explicitly given to you. The complexity is the same. That follows from follow-up work by Babichenko and Rubinstein, that even for a function that's just explicitly given as a polynomial, the complexity is the same. So the result is, robust to the respect to the representation of the function. So not the fact that it's a circuit that makes it hard. Mm-hmm.
The fact, did you say that? So if gradient descent is in PLS, you said, I guess, that local max cut is PLS complete. Doesn't it suggest that we should only care about quadratic functions, maybe?
Care about? What do you mean by care about? For applications or for what?
So maybe if we can do like, no, not for applications, like gradient descent only for quadratic functions, white box quadratic functions might be as hard as just gradient descent for all arithmetic circuits.
It might be, and this is actually a very interesting open question. But now we know that the problem is hard. The hardness holds for degree 5 polynomials. Decreasing the degree up to ideally degree 2 is a very interesting open question. Yes.
I mean, yeah. I guess maybe there is just like a black box argument that uses the fact that local max cut is PLS complete, right?
For quadratic functions, derivative will be linear.
Yeah. Okay.
Yeah, but still,
That's okay.
it's still like not clear at all how to find the stationary point.
Yeah, I would say the reasonable conjecture is still to expect that the quadratic gradient descent problem will have the same complexity as a general gradient descent problem, but it hasn't been shown yet. But of course, it's still very fresh, so hopefully in the coming years that will be resolved as well. Are there any other questions? Okay, so this intersection of PPAD and PLS, where we just saw that our gradient descent problem lies in that, it has actually been studied before. So Daskalakis and Papadimitriou, around 10 years ago, they noticed that there are a lot of natural interesting problems that lie in this intersection. And they gave a list of them, and they proved that they lie in this intersection. The contraction problem that we saw earlier, find essentially a fixed point guaranteed by Banach's fixed point theorem. The problem of finding a mixed Nash equilibrium of a congestion game, as opposed to a pure Nash equilibrium, where we know that the problem is PLS complete. The problem of solving so-called P-matrix linear complementarity problem, PLCP, which is can be viewed as a generalization of linear programming. The problem of finding fixed point guaranteed by Tarski's fixed point theorem. The problem of finding, rather of solving simple stochastic games, etc. So there are a lot of problems that occur naturally that turn out to lie in this intersection. And now, none of these problems can be PPAD hard or PLS hard unless some kind of collapse happens here, unless PPAD is a subset of PLS or unless PLS is a subset of PPAD. And for various reasons, it's not believed that this should be the case. In particular, there are oracle separations. Now, the next best thing one could hope for is, okay, let's show that these problems are complete for this intersection, that they are PPAD intersection PLS complete, as hard as any other problem in this class here. And so Daskalakis and Papadimitriou observed that this class, PPAD intersection PLS, seems to only have very artificial complete problems. So let me briefly explain this argument. So let A be any PPAD complete problem, for example, Nash, and let B be any PLS complete problem, for example, local max cut. And now I construct the following problem out of these problems, the problem either solution of A or B. And this problem is simply, I give you an instance of A and an instance of B, and you have to solve either of them, whichever way you want. So you're given an instance of each of the problems, and you're just required to solve one of them. Doesn't matter which one. Now, it's not too hard to see that this problem is automatically PPAD intersection PLS complete. And in fact, this is not an argument that's specific to PPAD or PLS. You take any two TFNP subclasses. If you construct this problem, it will be complete for the intersection of the two subclasses. So that's great. We already have a ton of PPAD intersection PLS complete problems. But the problem is these problems are very artificial. You've just taken two unrelated problems and put them together in this unnatural way. So let's look at a more specific example. Let's say for the problem A, the PPAD complete problem, I just take the Brouwer problem. What is the Brouwer problem? I give you a continuous function f from the unit hypercube itself, and the goal is to find a fixed point of the function, namely a point x, such that f of x equals x. And when you define this formally, you actually have to add a precision parameter and look for an approximate fixed point. But that's a detail here, it's not important. And so this problem is known to be PPAD complete. For the problem B, the PLS complete problem, we're going to take the following problem, which is called real local opt. Here the input consists of two functions. First of all, a continuous function P on the unit hypercube that you can think of a potential that we'd like to minimize. And then we're also given a function G that is possibly non-continuous. And you can think of this function G as an improvement function, namely as a function that we're going to use to find a better point for P. And so how is the solution concept defined here? It's essentially find the local minimum of P with respect to G. What does that mean formally? It means find the point X, but the potential value, if we apply G, is greater than if we just stay at X. And again, when we formalize this, we have to add a small epsilon there. But this essentially, you can think of this as a local search with the help of G, essentially. Trying to minimize P with the help of G. And if you end up at a point where G no longer helps you to optimize it, that is a solution. So this is known to be PLS complete. And so by the previous slide, it follows that the problem either solution for our real local opt is complete for this class PPAD intersection PLS. Now, of course, this problem is weird because I've just taken two unrelated problems, glued them together in an artificial way. And the problem that you get at the end, it doesn't look like anything natural. And so what Daskalakis and Papadimitriou said is, looking at these two problems, there's a much more natural way to merge them into a single problem. And that is to do the following: define continuous local opt. So if you stare at this, it's actually the same as real local opt. The only difference is that I also require the function G to be continuous now. That's the only difference. So again, I'm just trying to minimize the potential P with the help of this function G, but now this function G is also continuous. And it turns out that this problem, continuous local opt, as it's called, is both a special case of real local opt. That's obvious because we just added a constraint on G to also be continuous. But this problem is also a special case of the Brouwer problem. Why? Because if you find a fixed point of G, then you have also solved this problem. And so what Daskalakis and Papadimitriou argued is the way in which you combine this PPAD complete and this PLS complete problem into one to obtain this problem is much more natural than what happens in this either solution problem. And so they said, okay, let's define a class based on this problem. What does that mean? Let's define the class of all problems that reduce in polynomial time to continuous local opt. And let's call this class continuous local search, CLS. So if we take a look at the picture, I've zoomed in even further now, just into the intersection of PPAD and PLS. And we have the complete problems, the only complete problems that we know for PPAD intersection PLS. And so Daskalakis and Papadimitriou, they define this class CLS, which is defined using the complete problem continuous local opt. And what they did is they looked at various of these natural problems that lie in PPAD intersection PLS, and they showed that they actually lie in CLS as well. So I've put some of them here: contraction, simple stochastic games, etc. They all lie in CLS. And they then made the argument CLS has a much more natural definition than PPAD intersection PLS. And so it is more likely to capture the complexity of these problems. And by proving that these problems lie in CLS, they provided some evidence for that. Now, that was 10 years ago. And since then, there haven't been really any problems proved CLS complete, except one that I'm going to mention, which is a problem called Banach. Banach is a very general version of Banach's fixed point theorem, where you're not only given the function in the input as a circuit, but you're also given the metric as a circuit in the input, the metric with respect to which the function is contracting. So it's a very, very general version of Banach, and perhaps a bit too general compared to what the problems we usually care about, which is contraction, where the metric is just some standard LP norm. So in short, what I'm trying to say is this class CLS is much more natural than PPAD intersection PLS. It does contain all these problems, but over the past 10 years, there's been a little progress here because it's hard to work with the definition of CLS. So what happens to our gradient descent problem? Where do we put it in this picture over here? So I've just copy pasted the continuous local opt definition here. And let's look at one of the formulations, one of the equivalent formulations of our gradient descent problem, which is the local search formulation. And if you just stare at it for long enough, it's not too hard to see that this GD local search problem is just a special case of the continuous local opt problem. In other words, the function P that you're trying to minimize here is just a function F, and this function G that's supposed to help you in that It's just the gradient update rule, the gradient descent update rule. So it's straightforward to view this gradient descent local search problem just as a special case of this continuous local log problem. And what that means is that gradient descent, the problem lies in CLS even, not only in PPAD intersection PLS, but actually in CLS. And so the surprising result that we were able to show is that this gradient descent problem is not only complete for CLS, but actually even for PPAD intersection PLS. And so this immediately implies a collapse. Namely, it means that actually these two classes are the same. Namely, PPAD intersection PLS turns out to be the same as CLS. And it has, these ugly either solution problems that are complete for it, but also the gradient descent problem is complete for it, the continuous local opt problem, and this very general Banach. And the class, of course, contains all these problems. So what are the consequences of this collapse? Let me briefly discuss that. The first one is that surprisingly, it turns out that PPAD intersection PLS is actually an interesting class, even though at a first glance, it seems like, oh, it only has these weird artificial complete problems. No, actually, it has very natural and interesting complete problems. And it also has a nice interpretation. You can think of this class as the class where all problems that contains all problems that can be solved by gradient descent. Not necessarily efficiently, but where applying gradient descent algorithm will ultimately get you to a solution. Just like you can think of PPAD as being the class that contains all the problems that you can solve by using some algorithm for solving Brouwer. You can think of CLS, which is the same as PPAD intersection PLS, as a class that contains all problems that you can use gradient descent to solve them. There are also some more technical consequences. It turns out that actually two-dimensional versions of these problems are already as hard as the higher dimensions. The hardness holds even for very simple domains, simple arithmetic circuits, etc. So in the remainder of this talk, I will present a proof sketch. So maybe let me ask if there are any questions until now.
Can I ask, in the two-dimensional version, does the input size come mainly from the circuit?
Or the epsilon?
Epsilon?
So our hardness result is for a circuit, as I said. And so the hardness will come both from the circuit and the epsilon. The result that I mentioned, that the problem remains hard even for explicit polynomials of degree 5, that result holds only in high dimension. So a polynomial of many variables, of n variables. Otherwise, the problem would be easy. Does that answer the question?
Yes, thank you.
Great. Any other questions? Okay, let me start with a proof sketch, and you can interrupt me at any point anyway. All right, the proof sketch. Proof sketch of what? Proof sketch of the main theorem. So what is the main theorem? The main theorem is that this gradient descent problem that we study is PPAD intersection PLS hard. So what do we need to do in order to show this? We need to provide a polynomial time reduction from a PPAD intersection PLS hard problem to the gradient descent problem. So we don't really have a choice there. The only PPAD intersection PLS hard problems that we know, complete problems that we know, are these either solution artificial problems. And so that's what we're going to do. We're going to take an either solution problem with some PPAD complete problem and PLS complete problem, which I'll tell you more about in a bit. And we're going to reduce it to the gradient descent problem. And as I told you, the hardness result even holds for the two-dimensional version. So we're actually going to reduce just to the two-dimensional version of the gradient descent problem. Very high overview of how the reduction works. So we work on a domain which is just a unit square, 2-dimensional, and we're going to use the instance of either solution that we have to construct the values of f and the gradient of f on a very fine grid over this unit square domain.
Fine would be
Then-
exponential in 1/epsilon.
Yes, it's going to be very small. I mean, how small it is will depend on essentially the PPAD and the PLS problem. So this is the first step, define it on a discrete grid. And then we're going to use a special kind of interpolation, which is called bicubic interpolation, which is going to turn this discretely defined function into a smooth function over the whole domain. And the usage of this bicubic interpolation will ensure that the function we obtain at the end is continuously differentiable. So it is sufficiently smooth, which we need. And then the third step is just to prove that any gradient descent solution of f, in other words, any stationary point of f, from it you can extract a solution either to the PPAD problem or to the PLS problem. And if we have all of these things, then we have provided a reduction. So I'm not going to go into detail about how these things work, but the point is just to present the intuitive ideas behind the reduction. And in order to do that, I will start by defining PPAD. So what is PPAD? The class PPAD is defined by using a canonical complete problem, which is called end of line. In other words, the class is defined as all TFNP problems that reduce in polynomial time to this canonical complete problem. So what is this end of line problem? In the end of line problem, you're given in the input a directed graph of paths and cycles. So in other words, every vertex at out degree at most 1 and in degree at most 1, and you're given a source. So let's take a look at it. This is a graph where every vertex has out degree at most 1 and in degree at most 1. As a result, there are only paths and cycles. And so you're given a graph like this, and you're also given one source, one specific source of the graph, which I've put as a blue square over here. And what is the goal? The goal is to find
that it's an exponentially large graph.
Yes, yes, exactly. That's the catch. I'll get to that in a second. And so the goal is to find a sink of the graph or another source. So any of those red stars are valid solutions. Of course, this problem would be easy if you were just given the graph explicitly in the input. So there is a catch. And the catch is that the graph is given to you implicitly. Namely, the vertex set is all bit strings of length n, and you're given Boolean circuits S and P that compute the successor and predecessor in this graph. What I mean by that? Well, if you input this vertex into the successor circuit, it would tell you this guy over here is a successor. And if you input this bit string into the predecessor circuit, it will tell you this is a predecessor. So intuitively, the idea is you can explore the graph efficiently. Maybe you can take steps, single steps in the graph efficiently. You can take one step in the graph efficiently, but the size of the graph can be exponential in its representation. And that is what makes the problem non-trivial to solve. Let me ask if there are any questions about the definition of the problem.
How are you guaranteed that it is not, I don't know, only cycles?
So because you're given a source, right, in the input,
Okay.
It's guaranteed that there will exist at least one sink, and that's why there exists always at least one solution. Otherwise, the problem would not be TFNP. So that's why it's important that you're also given the source in the input, so that you know there has to exist a solution. There's no way, there's no solution. Okay, let me move on then. So the intuition of the reduction, we're going to reduce from the either solution problem, where the PPAD complete problem will be the problem we just saw, end of line, and we'll use some other PLS complete problem, which I won't mention explicitly what it is. And so the goal is, given an instance of this, construct the gradient descent function. So we need to construct a continuously differentiable function f, such that any gradient descent fixed point is a solution to the either solution instance. So the function will be defined over the unit square domain. And as a starting point, we're going to start with a very simple function, which we'll then modify locally. So the function that we start with is a function that I represent by this. So the direction of the arrows here is the direction of gradient descent. In other words, if I were to do gradient descent at this point, in which direction would I go? In other words, it's minus the direction of the gradient. And so if the gradient, gradient descent pushes you in this direction everywhere on the domain, then the only gradient descent solution is the origin 0, 0 down here. And if you want to picture this as an actual function, it corresponds to a function like this. Okay, so you have the domain down here, x and y, and you have the function value, which is the height. And this function here, this very simple function, corresponds to what I represent here, namely that gradient descent just pushes you in this direction everywhere. And as a result, the only stationary point, the only gradient descent point is the point down here. So this is going to be a starting point. Obviously, finding a stationary point here is easy because we know it's there. So we take this, let's say, base function, and now I'm going to perform local modifications. And it turns out that one thing you can do is you can take this stationary point that lies at the origin, and you can hide it somewhere inside the instance. How do you do that? You do that by creating this green path, where again, the arrows represent the direction that gradient descent takes. And you should think of this green path as being a very deep valley, namely the function value is much lower than anything around it. So if we go back to the picture of the function, you should think of it as we're going to dig a deep valley starting here and going somewhere into the domain. And as we go forward inside this valley, it becomes deeper and deeper. And as a result, this actually achieves what we want, namely hiding this trivial solution here, hiding it at the end of this path. So this is
so
one.
0, 0, 0 will be the source given to you in the PPAD instance.
That's how it will be in the reduction, yes. So this start of a path here that we can create in our function will essentially correspond to the source of the end of line instance, exactly. So already just with this technique, we can already show a partial result by considering a special case of the end of line problem, which I call the monotone end of line problem. And this is the case where the vertices of the end of line problem are numbered from 0 to the n, and edges are only allowed to go forward, namely from a lower numbered vertex to a higher numbered vertex. In other words, this is just the end of line problem, but with more structure. There's some kind of monotonicity in terms of the edges. They can only go from lower numbered vertices to higher numbered vertices. Other than that, the problem is still the same. You're still just given some source, 0, and you have to find any sink or any other source. So in this example, 2 would be a solution, 4 would be a solution, and 7 would also be a solution. But you have this added structure that the edges can only go forward. Now, we can actually reduce from this problem already with the techniques that we have. What do? So we take these vertices from 0 to 7 in this example, and we think of them as lying on the diagonal of the domain. And then we use this trick with the encoding of a path with a valley to encode every edge of this instance. And the rest of the function will just be the function as before. In other words, we take this original base function and we modify it locally to embed each of the edges of this monotone end of line instance. And because we saw that we can create a valley at the origin, that will essentially create the edge that goes out of the source that we're given. And then here at 1, we have a valley coming in and a valley coming out. So we can just connect those two valleys. So it's just like the continuation of a valley. And as a result, it turns out that the stationary points now will only be at the end of valleys or at the beginning of valleys as well. You cannot just begin a valley anywhere. You have to pay for it by also lying a solution there. But that's fine because other sources are also solution for us. So In other words, we get a reduction because any sink or source of a valley corresponds to a sink or source of the monotone end of line problem. Bit of a subtle point you might wonder about: what happens on the crossings here, right? You have two valleys that cross. Is that a problem? It turns out that there's a standard trick in the literature to fix this, which is to locally reroute the valleys so that there's a valley coming from down here. Instead of continuing up there, it will turn right into this valley. And the valley that came from the left, instead of going straight into this valley, will turn left into this valley. And then you have no longer have a crossing. And even though that changes the topology of the graph, because you have locally rerouted edges, it doesn't change sources or sinks of the graph. That was just a minor detail that I wanted to mention in case someone was wondering about this. So this provides a reduction from this monotone end of line instance.
But as you're doing it, you have to have some control of the Lipschitz function, Lipschitz constant of the function you're building here, right?
Yes. So remember, what we actually do is that we define the function and the gradient value on a very fine grid, and then we use this interpolation. And so the type of interpolation that we use and how different the function values are will have an influence on the Lipschitz constant of the function.
I guess the point is that you have like the liberty to get far away from the diagonal. So this is why you can, I mean, otherwise it seems, okay, maybe let's wait for the construct.
No, but it's true. There will be a big differential of value between because this valley is really deep, right? By the time the valley has gotten here, it's going to be really deep. Whereas the surrounding function value,
if there is too much accumulation of values near one point, it seems like you'll run into a problem.
It turns out that just doing this, let's say the naive way, already gives you the hardness result. And in terms of the parameters, I think there's no hope of improving the hardness result because gradient descent is otherwise gradient descent solves the problem easily if epsilon is not inversely exponential. Any other questions about this first partial reduction?
Yes, how do you construct this type of thing as a circuit, like using the previous circuits and not actually looking at the entire thing?
Yes, exactly. So it turns out that you can construct this thing locally, and this is essentially already known by techniques by Hubacek and Yogev. So the idea is, okay, you have what you're given the Boolean circuits of the end of line instance that compute the forward and backward edges. And that's actually all you need in order to create this embedding. Why is that? If I look at a point here, how do I know what should happen here? If there's a valley going through or not? How do I know? Well, I have to check if there's an outgoing edge out of 4 coming through here, or if there's an incoming edge into 6. Those are the only things that can cross here. And so that's just a constant number of things to check. And that's why you can efficiently check and know what the function of the value is going to be here. And what that means is that you can construct a circuit that computes the function value and the gradient on a discrete grid. And then you're going to use that to do the interpolation.
Yeah,
and the fact that you can locally...
You also have the crossings, so you don't need something about...
Sorry, can you repeat that?
Do the crossing, like dealing with the crossings, does that not change what you just said?
So the crossing again is the same, right? You just here, and if it happens, okay, let's go back to the point where I was here, right? 4 or 6. What happens if I check if something is coming out of 4, and maybe there's something coming out of 4 and going to 7. And I also check if there's something coming into 6, and maybe there's something coming in from 3 and going into 6. But then I know what to do locally, right? The crossing, the trick to resolve the crossings is also a local trick. So I know I just have to apply the crossing trick here locally. And this doesn't have any impact on anything else on the instance. It's really a local local modification, this crossing trick.
Well,
In other words,
it doesn't propagate. I mean, fixing a crossing at one point may not create a crossing at a nearby point and so on.
No, exactly. Because at any point you can have at most two paths going there. Fixing the crossings is just a completely local change. It's just a local rerouting that doesn't have any impact whatsoever on the rest of the instance. Nowhere. And this is important, obviously, otherwise it will be problematic. The fact that you can do everything locally, determine what, whether there's a valley going through in what direction, what function value, if there's a crossing you need to handle or not, everything is locally computable. Any other questions? And one thing that's important about this is that the depth of a valley only depends on where it lies in this domain. That's why you can do this rerouting locally. Everything can be done locally. That's the message. So this is a first reduction, but of course now we've only reduced from this, special case of end of line. What happens if we try to reduce from the standard general end of line problem? So obviously we can still number the vertices from 0 to the n, 0 being the source that we're given, and we're going to have edges, but we no longer have the guarantee that the edges are all forward edges. So we will also have what I call backward edges. And so I'm going to color the edges, the forward edges green and the backward edges red here. So there are two types of edges, and I will handle those differently. So the first thing we can do is just focus on the forward edges. And by the previous reduction, we essentially know how to handle those. So we know how to take our base function, modify it locally by introducing these valleys, so that we have embedded essentially these green paths. Now, of course, if we were to just stop here, 4, 5, and 7 would be solutions, even though in the original end of line instance, only 3 is a solution. That's the only solution. So this doesn't work. What do we need? Well, we need a way to embed the backwards edges, the red edges as well. And it turns out that there is a way to do this. You can introduce these red paths. So what are these red paths? What should you think about them? So first of all, notice that the direction of the arrows, which is again the gradient descent direction, is opposite to the direction of the edge. In other words, if you were to do gradient descent here, it would push you in this direction. And in terms of the function value, a red path is no longer a deep valley, it's the opposite. It's a very high mountain ridge, higher than the base function. So in a certain sense, it's kind of the symmetric opposite of the green paths. And it turns out that you can construct these. Again, everything is locally efficiently computable. And as a result, you can embed the red edges as well. Is that enough? Well, if that was enough, then we would have shown PPAD completeness, PPAD hardness, which we don't expect to show. So what goes wrong? Well, what goes wrong is that if you look at 7 here, you have a very deep valley coming in here, and you have this high mountain ridge. That means that there has to be a local minimum here at the end of the valley, because the valley, as we said, is much deeper than anything else. And so there's just going to be a local minimum there, which is going to be a stationary point. That's unavoidable. If we look at 5 here, which is kind of the symmetric case, what happens here? Where here we have this mountain ridge that's leaving like this, and the direction of the gradient descent tells us that this is the highest point of the mountain ridge. And that means that we will have a local maximum over here. And that's also unavoidable. And so it looks like we haven't really made any progress, except that now 3 is also a solution. But the unwanted solutions 4, 5, and 7 are still there. There will still be stationary points here. And this is the crucial point in the reduction. So let's zoom into 4, for example. So we have this green valley coming in and this red mountain ridge. And in this case, the valley is going down here. So there is a local minimum over here. And that will be a stationary point. this is unavoidable. So what can we do? What we can do is accept that there's going to be a solution there, but do our best to hide its exact position. And so in order to do this, we introduce a gadget that we call the PLS Labyrinth. And what the PLS Labyrinth does is that it takes this, obvious solution that has to be there, and it hides its exact position in such a way that locating the precise coordinates of where it lies requires you to solve the PLS problem that we were given in the input, namely the second part of the either solution instance. So what am I saying? The either solution problem gave us two instances, an instance of end of line, the PPAD complete problem, and an instance of the PLS complete problem. We used the PPAD complete problem to construct all of these paths, and there was this issue. And then we used a second problem to resolve the issue by hiding the solution using the PLS problem. And now what that means is that if you do this everywhere, whenever a red path meets a green path, you have this small PLS labyrinth there that hides the exact position of the solution. What does that mean? It means that if you look at it from up here, yes, there's still a stationary point at 3, 4, 5, 7. If you give me the stationary point at 3, then I've solved the end of line problem. I found a sink. If you give me the stationary point that lies somewhere here in 4, then the precise coordinates inside this thing are going to give me a solution to the PLS problem. And this is exactly what we wanted. We wanted any gradient descent solution, namely any stationary point, to give us a solution either to the PPAD problem or to the PLS problem. Because that's exactly what the either solution problem wants. A solution to one of the two, doesn't care which one. We cannot predict which one we'll get, but we'll get one of the two. This is really the crucial idea of the reduction and the main new idea of this paper. So now, what does the function actually look like? Well, I told you the way it's constructed is that we define it on a discrete grid, and this is supposed to be an example. So here you have a green path. This is a valley, and you have a red mountain ridge. The arrows point in the direction of gradient descent, and the colors encode the value of the function. You can ignore the numbers. The numbers just there to just count the number of different small templates that can occur. But this is essentially the idea of the reduction. So let me ask if there are any questions about this argument.
I have a little bit of a question, and this might, perhaps I'm not fully following. So to sort of deal with the fact that you have these cycles, you use your second problem to hide the point. And so I guess what's the finer detail that stops you from just removing the initial machinery, starting at the origin and just hiding the origin and just not dealing with the PPAD problem?
Yeah, that's a very good question. So because of the way, this is constructed, there is this path that always starts at the origin, as we saw. And now, how are you going to hide this path? What can you do? You cannot just make it disappear into a cycle, right? You can create a cycle like this on its own, that's fine. But the path that starts at the origin is still going to have to end somewhere, even if it goes through this inversion that turns it into a backwards edge. The path is never going to just disappear, right? And that's the reason why you always stay in PPAD, and you cannot just show PLS completeness. Does that make sense? It's just because of this initial path that you cannot just make it disappear. You cannot just close it on itself.
Well, another way of saying it maybe is that you cannot embed the PLS problem unless you have both green and red.
Exactly. That's a yes.
Again, there is just no way to embed this whatever labyrinth.
Exactly. You need both these paths here in order to construct this thing for it to work. So you cannot just put it at the end of the green path without a red path starting there afterwards. Whenever you put a PLS labyrinth at the end of some path, there is an opposite path that just jumps out. And that is indeed crucial. Otherwise, you would be able to show PLS completeness.
But why can't you embed it just at every point where there is a green edge, a local condition saying when a green edge is leaving and a red edge is coming in? This is something that you know from your circuit. Whenever you have this, you embed the PLS. Or maybe that's exactly what you're doing.
It is.
Yes, so we check locally when you're here in the region of node 4, you can check efficiently exactly what edge comes in and comes out, and you know if they're forward or backward edges. And as a result, you know whether you have to construct this whole thing here. This whole
Yeah, but I've been thinking even higher level before you embedded it in the two-dimensional grid. Just thinking about the graph. Every vertex which has a green edge leaving and a green and a red edge coming in will be the center of one labyrinth, right?
Mm-hmm. Yes, it will be the start point of a labyrinth. Yes. Mm-hmm.
So can you be more precise about the boundary conditions needed in order to be able to plant a labyrinth? Just one very low point and one very high point on the boundary of the yellow rectangle? This is what you need.
I mean, we haven't really investigated this formally, but the intuition is that you need to have this way of somewhere to throw away your potential to go into lower values and some way to throw away potential to go into higher values. You need to have these conditions that there is something that leads to higher values and something that leads to lower values from your gadget. So that's all I can say about this intuitive idea that you need those two things to construct it. And it seems like this makes sense for this to be necessary. But we've not investigated formally why it is necessary or stuff like that. Any other questions? We can get back to this anyway. So anyway, I just have some concluding remarks. So what are future directions? The first one is that there is a surprising result here that this intersection of classes PPAD and PLS turns out to be interesting, have natural complete problems, etc. Other intersections of classes, where you just take this intersection, which is kind of an artificial operation, and it turns out that it's something very natural with a very natural interpretation. And then more specific open questions. Can we show that other problems that lie in PPAD intersection PLS are actually complete for this class? And I've put some candidates here: the contraction problem, the problem of finding a Tarski fixed point, the problem of finding a mixed Nash equilibrium of congestion game. And actually, in the follow-up work by Babichenko and Rubinstein that I mentioned, was shown that this mixed congestion problem is indeed complete for PPAD intersection PLS. And this was shown by reducing from this two-dimensional gradient descent problem that I just showed you and that we just worked with, reducing from that to the problem of finding a mixed Nash equilibrium of a congestion game. And as a kind of a byproduct of that, they also obtained this result that I mentioned earlier, which is that the problem remains hard in high dimension with degree 5 polynomials. And it remains an open question to show that the hardness continues to hold even for lower degree of polynomials. This is all I had to say, or actually one more result, which is kind of related, yes. So all of this was for minimizing, for so-called min optimization. But there is a harder problem, which is called min-max optimization. And Daskalakis, Koulakis, and Zavetakis have studied the analogous questions for this setting, and there it turns out that the problem is PPAD complete, which kind of goes well with the general understanding that min-max optimization is harder than just min optimization. I know that's all I had to say, but I'm very happy to answer more questions.
Thank you very much.
Thank you.
So I had a
Hello?
question. The function that you constructed, like, what does the Lipschitz constant of that look like in comparison to like 1 over epsilon? So like at the end of this whole reduction.
Yes. So the ratio Lipschitz constant over epsilon, that needs to be exponential in the input. Otherwise, the problem can be solved efficiently by just doing gradient descent. So you cannot hope to get something better than exponential L over epsilon in this reduction. In terms of the exact parameters, I mean, then, you know, there's dependence on the size of the circuits of the end of line instance and the PLS instance. What I can say though, which is related to that, because obviously when you work on these white box problems, you don't care too much about the exact parameters. You know, as long as you can write them down in binary, you've shown hardness for the problem. It turns out that the same reduction here can be used to also study the black box complexity of the problem. In the model, you can just query the function value and its gradient. And so you can actually use this the same reduction to show the same best lower bound that we currently know. So in that sense, it feels like the reduction is pretty tight, at least.
Great. Okay, that makes sense. Thank you.
Thanks.
All question. So can you imagine if people looked at the natural classes of functions that are between convex functions and general continuous functions, for which this problem gradient descent, as you define it, will be easier?
That is a good question. No, I've not thought about this. And yeah, I'm not too familiar with intermediate classes of functions. I guess there must be stuff like that in the optimization literature.
I don't know what's your point, but Paul has a paper on star convex functions, which is some generalization.
That's right. Star convex is yeah. I'm not sure what I mean exactly in this framework, but right. So star convex. Well, also basically convex functions will work there, but yeah, I wonder if there is more general. Yeah,
that's interesting. I guess we don't know anything about this, even in the black box model, about these star convex functions.
Not to my knowledge. Yeah.
No, the geodesic convex work in the black box model, but you need the Hessian as well. Yeah.
The hyperbolic programming stuff is also there, but is that convex? I can't remember. Anyway,
I don't think so.
So that might be another example.
Yes, I guess this is just, you know, the first step, taking the vanilla gradient descent and looking at the most standard function class continuous differentiable. But now it does open up all these other questions. What happens if you restrict the function value? The function class. What happens if you consider other, you know, solution concept? What if it's a second order stationary point? Things like that. So we believe actually that the reduction that I presented here, we believe that a small modification of it can be used to show that finding a second order stationary point is PLS complete actually, which is interesting. This, you know, the separation stationary point easier than second order stationary point. And in some sense, finding a second order stationary point is just as hard as any discrete local optimization problem. It's no longer, somehow you've lost this continuity that made the problem easier.
All questions? Okay, thanks, Alex.
Thanks a lot.